Hello friends. So today we are going to solve the questions from the year 2020, and there are a total of 15 questions, and all these questions are from the mains only, and this is part 1, and obviously we are going to require part 2 to cover all the questions, and might be there a possibility that part 3 will be also required to cover all the questions from the year 2020. So in the first part we are only going to cover 15 questions, and all these questions are from the only mains. So the first question, it states that in a Young's double slit experiment, 15 fringes are observed on a small portion of screen when light of wavelength 500 nanometer is used. 10 fringes are observed on the same section of the screen when another light source of wavelength lambda is used. Then the value of lambda is in nanometer. So we are given, so we can just draw an approximate figure. Suppose this is a screen and we have two slits, slit S1 and slit S2, and it is mentioned that somewhere on this screen we are having 15 fringes when the wavelength of 500 nanometer is used. Okay, so let us suppose this is the region in which 15 fringes are there when we are using the wavelength of 500 nanometer, and within same, you can say, section, we are going to get 10 fringes, but now the wavelength is being used, that is our lambda, and we have to find out the lambda. It means one thing that will be common to both 10 fringes as well as 15 fringes will be the width of this fringe width rather, and which is can be represented nothing but by beta. So this beta will be same for 10 fringes and when the wavelength is lambda, and 15 fringes when the wavelength is 500 nanometer. So we are going to use this basic concept here, and we know that our fringe width that is denoted as beta is equal to lambda capital D upon small d, and here capital D is the distance between the slits and the screen, and small d is the distance between the slits, and all these information are given to us. And this we can say that each is having n number of, so let us multiply by number of fringes that are here n. So we can write this equation according to, you can say, two parts. In the first part we can write beta will be equal to our n1 lambda 1 capital D upon small d, and second we can write beta is equal to our m2 lambda 2 capital D upon small d. Let me denote this as beta 1 and beta 2, but we know that beta 1 and beta 2 are equal. Beta 1 is equal to beta 2, so therefore we can write n1 lambda 1 capital D upon small d is equal to n2, and we have this as lambda 2 capital D and small d, and here this capital D small d cancels out, therefore we get from here that n1 lambda 1 is equal to n2 lambda 2, and we need to find out lambda 2 that in the question is given as a lambda. So we can write that lambda is equal to lambda 2, and that will be equal to over n1 divided by n2 multiplied by lambda 1, and n1 is our 15, n2 is our 10, and lambda 1 is given as 500, and this goes by 0, and this will be equal to our 750 nanometers. Therefore we can say our lambda is equal to lambda 2, and that is equal to 750 nanometers. Therefore this is our 750. Next question. It states that in a double slit experiment, at a certain point on the screen, the path difference between the two interfering waves is 1/8 of the wavelength. The ratio of the intensity of light at that point to that at the center of the bright fringe is. So in this case, we have to find out the ratio of the intensity at a particular point, and this particular point is where the path difference is 1/8 of the wavelength and center of bright fringe. So here also we can just draw an approximate figure. So this is our suppose screen. We have two slits. This is our S1 and this is S2. This is center of the bright fringe, and here we know that formula for the center of bright fringe is our I is equal to I naught cos square delta lambda by 2. Okay. And at a particular point, let us suppose this is a point P, and at this particular point it says that the path difference, which is represented usually by delta of x, will be equal to lambda by 8. Okay. And we need to find out the ratio of the intensity. Okay, at the center the ratio is our the intensity is given by our I naught, and so we can, and suppose at point P this intensity is given as I. So we know the relationship between the I and I naught. Using that relationship we can find out their corresponding ratio. Okay. So we start from the given path difference. So we are given path difference, which is represented as delta of x is equal to lambda by 8. And from here we can write our phase difference. Phase difference delta of phi will be equal to, this is about 2 pi upon lambda multiplied by path difference, that is our delta of x. We substitute the values, we get phase difference is equal to 2 pi upon lambda, and this comes as lambda by 8. And here lambda and lambda goes away and 8 goes by 4. So we get this phase difference is our pi by 4. And the relationship between the intensities, you can say that our I will be equal to I naught, and this is our cos square and delta phi by 2. Delta phi we just found out, so we can write this as our I naught cos square, and this comes as pi by 8. And we need to ratio of I by I naught. So we can say I by I naught will be equal to cos square pi by 8, and this comes approximately at 0.853. So option number A is the correct one. Option A is correct. Next question. It states that in Young's double slit experiment, the separation between the slits is 0.15 millimeter. In the experiment, a source of light of wavelength 589 nanometer is used, and the interference pattern is observed on the screen kept 1.5 meter away. The separation between the successive bright fringes on the screen is. So we have to find out basically the fringe width indirectly. Okay. So we can just draw the approximate figure for that also. So this is slit S1 and this is slit S2, and we have a screen. This distance is given as capital D between the slits and screen, and the distance between the slits is given as small d. And we need to find out the separation between the successive fringes on the screen. Okay. And we can say that fringe width will be equal to lambda capital D divided by small d. So you can see that our fringe width, that is our beta, will equal lambda capital D upon small d. Lambda is our 589 into 10 to the power minus 9. Capital D is given to us as 1.5 meter, and small d is given as 0.15 millimeter, 10 to the power minus 3. So this gives us that our beta will be equal to 15, and 15 goes away. We are left with only 10, and 10 comes minus 8. Minus 8 is our minus 3. This comes as minus 5. So we are left with only 589 into 10 to the power minus 2 millimeters, or in terms of decimal we can say this is equal to 5.9 millimeters. So option number C is the correct one. Option C is correct. Next question. It states that the aperture diameter of a telescope is 5 meter. The separation between the moon and the earth is 4 into 10 to the power 5 kilometer. The light of wavelength of 5500 angstrom. The minimum separation between the objects on the surface of moon so that they are just resolved is close to. So we can just draw an approximate figure for this. So we have the minimum separation between the object surface of the moon. Okay, let us suppose there are two objects on the moon, and the distance between these points on the moon is, let us suppose, given as S, and we have this as a telescopic lens. So we can just and D is this portion, and this is given as theta. and this will be a small d. And we know that our theta will be equal to s upon small d. And we can just substitute the value of, so we can use that our theta is equal to our s upon small d, and that can be also written as 1.22 lambda upon capital D. And from here we can say our s will be equal to 1.22 lambda multiplied by small d divided by capital D. And we simply substitute the values, get s will be equal to 1.22, lambda is our 5500 angstrom, so this comes at 10 to the power minus 10. Small d is our 4 into 10 to the power 5 kilometers, so we can write this as 4 into 10 to the power 8, and capital D is our 5 meters, so divided by 5, and this goes by 11 is our, so you can say that this will be equal to 26840 divided by 5 into 10 to the power minus 2. Therefore we can get our s is approximately equal to 53.68 meters, and we can just approximate it equal to 60 meters. So option number A is the correct one. Option A is correct. Next question. It is given that a polarizer analyzer set is adjusted such that the intensity of light coming out of the analyzer is just 10% of the original intensity. Assuming that the polarizer analyzer set does not absorb any light, the angle by which the analyzer need to be rotated further to reduce the output intensity to be 0. Okay, so in this case, we can divide this entire discussion into two parts. In the first part, we are going to consider that the output of the analyzer is only 10% of the original intensity. Original intensity, suppose, is our I0. Okay, so the final output will be 10% of that. And in the second case, it says that, and based on that, we can find out the angle theta, that the position of the analyzer when the output is only 10% of the original intensity. In the second case, it says that we need this output intensity to be equal to 0. So the polarizer, the analyzer is need to be rotated further, and we need to find out this further rotation of the analyzer. So this is the basic premise of the question. So we can just draw approximate figure, and we have a unpolarized light, and suppose this is our polarizer P, and we have an analyzer denoted as A, and this analyzer, suppose, is at an angle of theta, so that our output is the 10% of the initial output. Okay, that is our initial intensity. Okay. So we can write that our I will be equal to our I naught, and we have this cos square of theta. Okay, so this is the intensity output of the A, and here our I naught is our maximum intensity. And it says that only we get the 10% of the intensity will be getting the output. So from here, according to the question, we can say our I will be equal to 10% of I naught, and therefore we can say our I will be equal to 10 upon 100 multiplied by I naught, or we can say our I will be equal to I naught divided by 10. Therefore, we substitute, let us suppose this call is equation 1. So we can say from equation 1, we can write that I naught upon 10 is equal to our I naught, and we have this cos square of theta. I naught and I naught cancels out, and we get cos of theta is equal to 1 upon square root of 10. So we get our theta is equal to cos inverse of 1 upon square root of 10, which is approximately equal to 71.6 degree. But it says that we want that the intensity should be equal to 0. So from the equation number 1, it is quite obvious when theta is equal to 90 degree, the intensity, that is I, comes equal to 0. You can say that for theta is equal to 90, equation 1, I is equal to 0. Okay, because cos 90 is equal to 0. So it means the extra rotation, so you can say further rotation of analyzer will be equal to 90 minus 71.6, and this comes as approximately equal to, let us call this as theta prime, and that will equal to 18.4. So we have 18.4, that is option number B is the correct one. Option B is correct. Next question. It states that in a double slit experiment, when a thin film of thickness T having a refractive index mu is introduced in front of one of the slits, the maximum at the center of the fringe pattern shift by one fringe width. The value of T is, lambda is the wavelength of the light used. So once again, we can use, or we can say we can divide this question into two parts. In the first part, when there is no thin film, and the second part when this thin film has been introduced. Okay. And the difference between the two is the shift, pattern shift of one fringe width, that is nothing but our beta. Okay. Or we can also find out the path difference based on this. So we can draw an approximate figure for both the cases. So case 1, when there is no this is a slit 1 and slit 2. We are having screen, and at the center, which will be our, you can say, the maximum bright, and that is a, here our, we can say this is our central bright, central bright, okay, this particular point. Now in case 2, we have introduced a thin film, suppose in S1, then we can just draw it. So we have case 2, and these are the two slits, S1 and S2. We have screen, and we have a thickness T and refractive index mu. Thus it's suppose introduced in the path of S1. Let us suppose this is point P, okay, and this is our central point. Now this P becomes our central bright. Let us call the central bright as CB. So this P becomes now CB, and this shift is said to be one bright fringe. Okay, one fringe width is the shift. And here also we can just draw a perpendicular, and let us call that this will be our delta of x, and this is our is equal to lambda, and let us call this length as L. So you can say that our for central bright fringe, at the position of first bright, so we can say our path difference, that is our S2P minus S1P, should be equal to 0, and we substitute the respective. So S2P will be our delta x plus L, and delta x is equal to lambda. So we can write this as lambda plus L minus, and that will be because of the this, you can say, thin glass film, you can say optical path length will be increased, and therefore we can write this as L minus T, and this will be plus mu multiplied by T is equal to 0. And now we can simply open the bracket. We get this as lambda plus L minus L, and we have this plus T minus mu T is equal to 0. And here this L and L cancels out, so we get from here that we can take this will be equal to lambda is equal to T mu minus 1, and we need to find out our T, so we can say our T is equal to lambda upon mu minus 1. So the option lambda upon mu minus 1, that our option C is the correct one. Option C is correct. Next question. And it states that in the figure below, P and Q are two equally intense coherent sources emitting radiation of wavelength 20 meter. The separation between P and Q is 5 meter and the phase of P is ahead that of Q by 90 degree. A, B, C are three distinct points of observation, each equidistant from the midpoint of PQ. The intensities of radiation at A, B, C will be in the ratio. And here we are given the basic figure. So we have two sources. One source is at P, let us call that S1, another one is our S2. And it says that they are equally intense but of the wavelength of 20 meter. And the distance between P and Q is given to us as 5 meter. So this is distance between the slits, which is given to us as 5 meter. And it is also given that this the distance, each equidistance from the midpoint of PQ. So midpoint of PQ, let us suppose we call this as O. So distance of OC is equal to OA is equal to OB. Okay. So we are also given that our OC is equal to OA and is equal to our OB. And we are given that there is a phase difference between the sources which are at P and Q. So first of all, we are going to use here two formulas. One is our phase difference, which will be dependent upon our path difference, and second we are going to use of the intensities. Okay. When intensities are, both of intensity are same. So let us consider these points one by one. So we can say path difference of point A, because of the two sources, path difference of point A, and the path difference will be equal to PA minus QA. PA minus QA, and that is obviously is equal to PQ. And PQ is given to us as a 5. Therefore, we can say our delta of XA is equal to 5 meters. Now we can write the phase difference at point A. Phase difference at point A, and this phase difference is because of the path difference, that is delta x of A. So we can write that our phase difference at A, let us suppose that is given delta phi of A, which will be equal to, we have this as 2 pi upon lambda multiplied by delta x of A. If we substitute the values, we get delta phi of A will be equal to 2 pi lambda is given to us as 20 multiplied by 5, and this 20 goes by 4 and this 4 goes by 2, so this we get is equal to pi by 2. Okay. But in the question we are already given that there is a phase difference between P and Q also. Okay. And that phase difference is pi by 2. Okay. Therefore, we can say that the distance between Q and A, the distance between Q and A is less than P and A. P and A. So from here we can say that our QA is less than our PA, and the phase difference is, we just found out, is pi by 2, and phase difference is pi by 2. But in the question we are also given that P leads by Q pi by 2. But we are given that P leads Q by pi by 2. So we are going to find out the net phase difference. You can say net phase difference, let us call that as delta phi net because of A, and that will be equal to pi by 2 minus pi by 2 is equal to 0. Now we are given that both P and Q have same intensity, and let us call these intensities as I naught. We are given that P and Q have same intensities. Therefore, let us assume that intensity of P is equal to intensity of Q, and that is equal to over I naught. Therefore, the net intensity at A, net intensity at A, let us call that as IA, will be equal to, we have this is I naught, that is because of IP, other I naught because of IQ, plus twice square root of I naught multiplied by I naught, and we have cos of our delta phi net, which is our 0. So we can just write the formula here. We can say our intensity will be equal to our IP plus IQ 2 square root of IP IQ and cos of delta phi net. And if we solve them, we are going to get that our IA cos 0 is 1, so this comes as I square will be I, and this comes as 2I, and that will be equal to 4I naught. So this is our 4I naught. Okay. And now we can solve for P, so for B. So we can say for point B, and this point B is equidistant from both P and Q, is equidistant from P and Q. Okay. Therefore, the path difference that is our delta x of B will be equal to 0, and the phase difference, that is our delta phi of B, will be also equal to 0. And there is a, we already know there is a path extra phase difference at P leads Q by pi by 2. So therefore, the net phase difference we can call this as phi net B will be equal to pi by 2. Similarly, we can find out intensity at B. You can say intensity at B let us suppose that is a IB, will be equal to our I naught plus 2 square root of I naught and cos of our pi by 2, cos pi by 2 0. So this term goes away, and we are left with our IB is equal to twice of I naught. IB is equal to twice of I naught. Now we are left with only one point. That point is our C point. So you can say for point C, the path difference that is our delta xc will be equal to our QC minus PC, and this QC minus PC will be also equal to PQ. So we can say this delta XC is equal to our PQ, which will be equal to 5 meters, and the phase difference delta phi C will be equal to 2 pi upon lambda and multiply by our delta xc. So this comes 2 pi upon lambda is about 20 and multiply by 5. So this 5 goes by 4 and this 4 goes by 2. So we get our delta phi C is equal to pi by 2. And here we can say that there is extra phase difference because of the phase difference between P and Q. But the point C is closer to P than it is closer to Q. You can say our PC is greater than QC. Therefore, delta phi net of C will be equal to pi by 2 plus pi by 2, and that will be our pi. Now we can find out the intensity at C. Intensity at C, that is IC I naught plus twice I naught into I naught, and we have this cos of pi, and cos of pi is our -1. So we get our IC will be equal to 2I naught minus 2I naught, which gives our IC is equal to 0. And we need to find out the ratio. So ratio intensity at A, intensity at B, and intensity at C will be equal to our 4I naught ratio 2I naught and to 0, which can be written as 2:1:0. So option number B is the correct one. Option B is correct. Next question. It is given two coherent source of sound S1 and S2 produce sound waves of same wavelength lambda, that is over 1 meter in phase. S1 and S2 are placed 1.5 meter apart. See figure. A listener located at L directly in front of S2 finds that the intensity is at the minimum when he is 2 meter away from S2. The listener moves away from S1, keeping his distance from S2 fixed. The adjacent maxima of intensity is observed when the listener is at a distance of D from S1. Then the value of D is. So we are given the basic figure is already given to us. We have two sources, S1 and S2. Distance between these two sources is 1.5 meter. And initially the listener is just in front of S2 at a distance of 2 meters. This is given to us 2 meters. And here it observes that it is having a minima. Now it moves such that the distance, let us call this as our L prime, from L to L prime, such that the distance between these two remain the same. And here L prime, it says it is having a maxima. And the distance between S1 and this L prime is given as D, which we are supposed to find out. So initially we are given that our S2L is equal to 2 meters. So we are given that our S2L is equal to 2 meters is given to us. And let us join this. So we can find out our S1L. Because this is right angle triangle. So we can easily find out this our S1L. So we can say our S1L will be equal to 2 square plus 1.5 whole square and its square root. This comes as 5.2, which is approximately equal to 2.5 meters. Okay, so the initial position of S1 distance of S1L is 2.5. So this comes as 2.5. Now we can find out the path difference between the two when it is at the position of L. So we can say that our path difference that is our delta of x will be equal to S1L minus S2L minus S1L, and our S2L is S1, my mistake, S1 and S2. So we have delta of x will be equal to 2.5 minus 2, which comes as 0.5, and for the position of L, this should be equal to L by 2. And the listener moves from L to L prime. So we say listener moves from L to L prime, and here it is given that first maxima appears. First maxima appears at L prime. And this we can also say is only possible if the path difference is integral multiple of wavelength. Integral multiple of wavelength. So which basically means that our delta of x should be equal to n times lambda, and for first the value of n is our 1, so this comes 1 multiplied by lambda and is equal to our lambda. And the path difference, that is our delta of x, we can say will be equal to delta of x is equal to, we have s1 l prime minus s2 l, and delta of x is equal to lambda, so we can say, and s1 l prime is our d, so we can say d minus 2 will be equal to lambda. Lambda is given to us as 1 meter, so this is equal to 1. Therefore we get our d is equal to 3 meters. So option number D is the correct one. Option D is correct. Next question. We are given two light waves having the same wavelength lambda in vacuum are in phase initially. Then the first wave travels a path L1 through a medium of refractiveness N1, while second wave travels a path of L2 through a medium of refractive index N2. After this, the phase difference between the two waves is equal to. So wavelength in the vacuum is given as lambda, and the path length of the wave, you can say, is given as L1 when it is traveling in the refractive index of N1. It is given as L2 when it travels through N2. So we can find out what will be their respective optical lengths. Then we can just find out their phase path difference, and that is going to help us to find out the phase difference. So we are given that the vacuum wavelength is given as lambda, and wavelength in first medium medium 1, sorry, not wavelength but path length. In medium 1 is our L1, and a refractive index of medium 1 is given as mu1. Similarly, we can write that path length of medium 2 is our L2, and refractive index of medium 2 is our mu2. So we can find out from here the optical length of medium 1 and optical length of medium 2. Optical length of medium 1 will be equal to L1 multiplied by mu1, and we can write optical length of medium 2 will be equal to L2 multiplied by mu2. From here we can find out the path difference. Path difference will be equal to, let us call this as optical length in 1, and we have optical length in 2. Therefore we can say that the optical length in minus optical length in 2. We substitute the values. We get this as mu1 L1 minus mu2 L2. From here, we can easily find out the path difference, phase difference, because we know that the phase difference that is our delta phi will be equal to 2 pi lambda multiplied by path difference, that is delta of x, which we just calculated. So this is our delta of x. We substitute it, we get delta of phi is equal to 2 pi upon lambda, and we have this as mu1 L1 minus mu2 L2. And the option number, we have this as refractive index is given as n1, not mu, my mistake. Okay, so let me write this answer in the correct format, that is phi is equal to 2 pi lambda, and this comes as n1 L1 minus n2 L2. Okay, so we have n1 L1 minus n2 L2, that option number C is the correct one. Option C is correct. Next question. We are given a Young's double slit experiment is performed using monochromatic light of wavelength lambda. The intensity light at a point on the screen where the path difference is lambda is k unit. The intensity of light at a point where the path difference is lambda by 6 is nk by 12, where n is an integer. The value of n is. So we are given 2 points, and on these 2 points we are given the path difference. And in the first case, the path difference is over k units, and the path difference is over lambda. In the second case, the path difference is lambda by 6, and the intensity is given as k, and another one is given as nk by 12. So we have to find out the value of n. So we can use the formula that intensity at any point if given as I will be equal to I naught, and we have this is cos square phi upon 2. Here phi is our phase difference. Phi is our phase difference, and which can be further written as 2 pi upon lambda and multiply by path difference. Path difference which is given as delta of x. So we are given that when the path difference is lambda, so we can say for delta of x is equal to lambda, we are given the phase difference, that is, let us suppose phi 1, and this is called as delta x1. Phi 1 is given as k units. Sorry, not k unit. Okay, and the phi 1 will be equal to 2 pi by lambda multiplied by delta x1, which comes as 2 pi upon lambda multiplied by lambda, and here lambda and lambda goes away, so we get phi 1, that is the phase difference, will be equal to 2 pi. And in the second case, we are given that for path difference of lambda by 6, phase difference will be equal to 2 pi by lambda multiplied by lambda by 6, and we get this lambda and lambda goes away, 6 goes by 3, so we are left with this as pi by 3, and we can find out the intensity by putting this is our phi 2 and this is our delta 2. So let us call this as equation number 1. So we can say from equation 1 we can write our I1 is equal to I naught cos square phi 1 by 2, which comes as I naught cos square, this is our 2 pi upon 2. So we get our I1 will be equal to our I naught and cos square of pi, and cos pi is -1 square is +1, so we get here from I1 is equal to our I naught. Similarly, we can do it for I2 also. I2 will be equal to I naught cos square, and it is pi by 3, so this comes as phi 2 divided by 2 is equal to I naught cos square pi by 3 will be giving us pi by 6. Pi by 6, and from here this will be equal to our cos square pi by 6, and we have this as I naught, so we are going to get this as I naught multiply by, and we have this as 3 by 4. Now we can simply find out the ratio. So we can say our I1 upon I2 will be equal to I naught divided by, and we have this as I naught multiplied by 3 by 4. I naught and I naught goes away. This comes as 4 by 3. Or we can say our I2 will be equal to, I1 is given to us as K, I1 is K, so this comes as 3K by 4. We get from here that our I2 is equal to 3K by 4, but we are also given that our I2 is NK by 12, which is equal to NK by 12. And in order to make it equal, we can just sort it out, and we can write this as 3K by 4 divide and multiply by 3, giving us NK, giving us 9K by 12, which is equal to NK by 12. Therefore, value of N is equal to 9. Value of N is equal to 9. Next question. We are given, in a Young's double slit experiment, light of 500 nanometer is used to produce an interference pattern. When the distance between the slits is 0.5 millimeter, the angular width of the fringe formed on the distant screen is close to. So here we have to find out the angular width, and that is based directly on the formula that theta is equal to lambda divided by small d. Small d is the distance between slits, which is given as 0.5 0.05 m lambda is our wavelength. So this comes as 500 into 10 to the power minus 9, and this is our 0.05 into 10 to the power minus 3, and this comes approximately equal to 0.57 degrees, or this comes approximately equal to 0.01 radians, and now it will be coming as 0.57 degrees. Option number B is the correct one. Option B is correct. Next question. States that the interference fringes are observed on the screen by illuminating two thin slits S1, two thin slits 1 meter apart with a light source lambda 632.8 nanometer. The distance between the screen and the slits is 100 centimeter. If a bright fringe is observed on the screen at a distance of 1.2 millimeter from the central bright fringe, then the path difference between the waves which are reaching this point from the slits is close to. So here let us draw an approximate figure. So we are given two slits. This is S1 and this is S2, and on the screen there is a point P. Okay. And it says that is obtained at a distance of bright fringe at a distance of 1.27 millimeter from the central bright fringe. So we can approximately, so this will be our central bright fringe, and this distance is given as 1.27 millimeter. And it says that we have to find out the path difference between the waves. Okay. So if we draw a perpendicular, so this is the path difference, and we are supposed to find out this delta of x, and this is a capital D, and the distance between the slits is given as small d. And we can use the approximation that our small d is very much less than capital D, therefore sine of theta is approximately equal to theta. And we can just also draw the theta, so this will be our theta, or with respect to this we can also plot that this will be our theta. So we can say the path difference let us suppose that is our delta of x will be equal to d sine of theta, and we can approximate it by d of theta. And y, we already, this is our y is given to us, so we can say the path difference we can also write will be equal to, that is our delta of x will be equal to our y multiplied by small d divided by capital D. And we get this as, one second, yeah, and y is given to us, that is 1.27. Small d is also given to us, is our 1.27 millimeter. This is 1.27. Y is 1.27. One second. oh sorry, it is 1 millimeter. Okay. So this comes as 10 to the power minus 3 and divided by 1, and approximately that will be coming as 1.27 micrometer. Okay. Because I missed, this is given as 1.27 into 10 to the power minus 3 meters. So it is 1.27 micrometers. So option number A is the correct one. Option A is correct. Next question. We are given in the Young's double slit experiment, 16 fringes are observed in a certain segment of screen when the light of wavelength 700 nanometer is used. If the wavelength of the light is changed to 400 nanometer, the number of fringes observed in the same segment of the screen would be. It means the fringe width in both the cases is same. So we can just draw an approximate figure, and these are the two slits, S1 and S2, and this is a screen, capital D distance, and the distance between the slit is given as small d, and it says that certain segment of screen, so we can assume any segment. Let us suppose this is the segment, and within segment we are given 16 fringes, and when the wavelength is our 700 nanometer, and it says that we have to find out the fringes. Let us suppose there are n fringes within same segment and the wavelength is 400. Okay, so this will be beta, that will be same for both. Therefore we can use the formula that our beta will be equal to n1 d lambda 1 upon small d will be equal to n2 d lambda 2 upon small d. Here this d and d cancels out, and we get from here n1 lambda 1 is equal to n2 lambda 2, and we need to find out our n2. Therefore we can write that our n2 will be equal to n1 lambda 1 divided by lambda 2. n1 is 16, lambda 1 is our 700, and lambda 2 is our 400, and the 0 goes away, this 16 goes by 4, and this we get as n2 is equal to 28. So option number D is the correct one. Option D is correct. Next question, and it states that a beam of plane polarized light of large cross-sectional area and uniform intensity of 3.3 Weber per meter square falls normally on a polarizer, cross-sectional area 3 into 10 to the power minus 4, this is meter square, which rotates about its axis with an angular speed of 31.4 radian per second. The energy of light passing through the polarizer per revolution is close to. So here we are given a polarizer, and that polarizer is supposed to rotate with an angular speed of 31.4. So we can just draw the figure. So let us suppose this is our polarizer, and this polarizer is rotating in any direction and with the angular speed of 31.4, and we need to find out the energy of the light that is passing through the polarizer per revolution. Okay. But we know that if the polarizer is rotated by an angle of theta, then the intensity is given as I is equal to I naught cos square of theta. This we already know. Okay, and this here theta will be equal to omega multiplied by the time, that is t. So we are going to use this basic formula. So we can say that the intensity of transmitted light and that is given as a time dependent function, that is I of t will be equal to I naught cos square, and theta, that is also time dependent function, and here theta of t is equal to omega t. We substitute the value, we get our I of t is equal to I naught cos square, and we have this omega of t. And we need to find out the power transmitted to the polarizer, that will be equal to area multiplied by the intensity. We can say that power transmitted that is our P of t is equal to area multiplied by I of t. We substitute formula for I of t, we get our P of t is equal to our area I naught cos square omega t, and we need to find out the energy transmitted in per revolution. So we can write that energy transmitted per revolution and suppose the time period is given as capital T. So we can say that one revolution capital T will be equal to 2 pi upon omega. Therefore, we can write that our energy will be equal to integral of 0 to capital T P of t, that is power transmitted, and derivative of t. We substitute the value 0 of t, we have this as a I naught cos square omega of t, and this is our dt. And cos square omega of t, we can write it in a double angle form. We can write that our cos square omega of t is equal to 1 plus cos, and we have this is 2 omega t divided by 2. We substitute the value, we get our E will be equal to, we have our a I naught divided by 2, 0 to t, and this comes as 1 plus cos of 2 omega t, and this is our dt. Okay. But the integral of this cos 2 omega t will be equal to 0 for one full period. Okay. So this will be coming equal to 0. So we can just directly write it as our E will be equal to our a I naught divided by 2, and this comes as integral of 0 to t, and this is dt, which is our a I naught divided by 2 multiplied by capital T. And all the things capital T we can just replace with respect to omega. So we get this as a I naught divided by 2, and this comes as 2 pi by omega. and here 2 and 2 goes away, and we can just substitute the values. We get E area is given to us 3 into 10 to the power minus 4, and I naught is our 3.3, and pi is our pi, and omega is given as 31.4. So we can say, and pi, let me substitute pi also. Pi we can say is our 22.7, 22 by 7. So we get our energy E will be approximately equal to 9.9 into 10 to the power minus 5 joules, and we can further approximate it that our E is approximately equal to 10 into 10 to the power minus 5 joules and approximately equal to 1 into 10 to the power minus 4 joules. So the option number B is the correct one. Option B is correct. Next question. It states that origin light of wavelength 6000 in 10 to the power minus 10 meters illuminates a single slit of width 0.6 into 10 to the power minus 4 meter. The maximum possible number of diffractions minima produced on both sides of the central maxima is. So here we have a, you can say, single slit of width is given, and we know that for diffraction minima d sine of theta is equal to n times lambda, and value of L is nothing but order of minima, which is equal to 1, 2, 3 and so on. So we start from the basic formula, and which states that for diffraction minima we have d sine of theta is equal to n times lambda, where this n is our order of minima and values are 1, 2, 3 and so on. And it says that we are having a and from here we can write that our sine of theta will be equal to n lambda divided by 2, and for we need that the maximum possible, and maximum possible is only when our sine of theta is equal to 1. So we can say n will be maximum for sine of theta is equal to 1, because we want this n should be maximum. Therefore we can say that our n is equal to d upon lambda. D is already given to us, that is 6 into 10 to the power minus 5. Lambda is also given as 6 into 10 to the power minus 7. And 6 goes by 6, and this is 7 minus of 5, that comes as 10 to the power 2, which is our 100. And you can say this, so total number of minima on one side, you can say that total number of minima on one side will be equal to 99 and total will be on both sides will be 2 into 99, that comes as 198. So we have 198 will be total number of minima on both sides of the central maxima. So I think this completes all the questions. Yes. So this completes the part 1 from the year 2020 mains. Okay. So in this part we have already only considered mains questions. In part 2, that depends upon the number of questions. So if the number of questions are less, so that we can manage them in you can see in single video, then we are going to consider both mains as well as advanced. And if the number of questions on the higher side, then we have to do for a third part also, and then we are going to consider the advanced questions. So this completes the part 1. Thank you.